Previously, we saw that for exponential functions, they were one-to-one functions. Now, if we recall back to our previous information about one-to-one functions, we know that one-to-one functions have an inverse function. So that means for every exponential function, there is some inverse function, and the inverse functions of exponentials are called logarithmic functions. Particularly if we have an exponential function of the form f of x is equal to b to the x, then its inverse is something called log. This little subscript b is read base b of x. Let's talk about exactly what log base b of x is. If we have the equation y equals log, the subscript here is read base b, parentheses of x, it is asking the question, what exponent must we raise b to in order to get the final value of x? This translates to b to what power y would we have to raise to in order to end up with the value x. Now, one of the key hallmarks of exponential functions, inverse functions, is that the input of one is the output of the other, because we know the domain and ranges switch for functions and their inverses. So notice for the logarithm, x is the input of the logarithm, but do we see it's the output of the exponential? Y is the output of the logarithm, but it's the input of the exponential. And this matches our expectations that inverse functions should switch their domain and range or their input and output values. So whenever we see something like log base 2 of 32 equal to y, it's asking us what exponent on 2 is necessary to get the value 32. So 2 to what power would end up giving us 32. As we think through the powers of 2, we would realize that is 2 to the 5th power. So the value of the logarithm, log base 2 of 32, is equal to 5. So we want to keep in mind that logarithms are asking us what power must we raise the base to in order to get the value of the input. Now, log, if we ever see this, and maybe we should rewrite this a little more clearly, this is supposed to be log of 1000. And notice in this particular case, there's no base written here, like we'd be given to expect, like here we had a base 2. When there's no base written, it's implied that it's base 10. So, whenever there's not a base written, we know that's implied log base 10. And now let's translate this statement in terms of what it's saying about exponentials. Think about how you could fill in these blanks based on our knowledge of what this exponential says and the powers of 10 that we know. So what exponent on 10, the base, is necessary in order to end up with what we have as the input, 1000? So 10 to what power would give us with 1000? As we think through the powers of 10, we would realize that's 3, because 10 cubed equals 1000, so the value of t that we were looking for here is 3. Now with this, we can see that there's a real equivalency between an exponential function and a logarithmic function. If we have something expressed as log base b of c to the a, that is equivalent to an exponential equation where we keep the same base b, but we keep in mind these are inverse functions, so the input of one becomes the output of the other, and the output of one becomes the input of the other. That allows me to replace this with our c, and that with our a. So b to a's power would give me the value of c. Just like 10 cubed gives me 1,000, or 2 to the 5th gives me 32. So the key thing about logarithms is being able to go between these two expressions. Can you, given an expression, go between the logarithm and the exponential form? So this is one thing that you want to memorize and understand as soon as possible, how to go from a logarithm to an exponential. This will be foundational for our next few sections. So in our next example, we're asked to convert each exponential statement into an equivalent logarithmic statement. So we're given the exponential form, and then we need to turn it into a logarithm. And for our first example, we need to mention a bit of notation. Here we see our e again. Remember, this is the transcendental number that is at first approximated by 2.718 and continuing. So in our class, e is never representing a variable. It's always representing that number. And logarithms with base b are so common and useful that we give a special notation for the logarithm base b. So just off to the side, let's make a note. If we want to express log base e of x, this is so commonly used that it's given a special name, ln, which we would say is natural log of x. So just like if we have log base 10, we don't write the base 10, it's just implied. If you see ln of x, that's implied to be log base e of x. So we would write our logarithm, we would have ln of some input equals some output. And we keep in mind that exponentials and logarithms are inverses, so we have our base e here. That's where the base went. And remember, the input of the exponential becomes the output of the logarithm. The output of the exponential becomes the input to the logarithm. So we'd have ln of 10 is equal to the value of b. And if we wanted to, we could actually find this as a numerical value if we go to our calculators. I can see here I've got my natural log button there, so I'd have ln of 10, and that's about 2.30 when rounded. So b is the value about 2.3. So similarly, take a moment to convert this exponential expression into a logarithm. I recommend you would pause the video, unpause when you're ready to check your work. Now here our base is 3.6, so we would have log base 3.2, sorry, not 6, of the output of y. That whole value is equal to the original input of 6. Now for our next expression, we can't calculate it unless we're raising the entire input to an exponent. So right now this is 2 times x to the negative 5th. Notice the exponent is only going to the x. So before we can write as a logarithm, we would first need to solve to get only on one side the variable to the exponent, or the base to the exponent. So I would begin by dividing both sides by 2, and we would get x to the negative 5th equals 6. Now we can rewrite this as a logarithm. Our base is x, so we'd have log base x of, remember, the output of the exponential becomes the input of the logarithm, is equal to the input of the exponential is the output of the logarithm, negative 5. Now we're going to go in the reverse direction. In this case, we are going to start with logarithms, and then we're going to express them as exponential functions. So in our previous example, we went from exponentials to logarithms, now logarithms to exponentials. So here we have log base b of 2 equals 3, so we keep the base the same, but remember the output of the logarithm becomes the input of the exponential. So this is going to be b cubed would be equal to the value 2, because the input to the logarithm becomes the output to the exponential. Now why don't you take a moment and pause this video and attempt both B and C on your own. Unpause to check your work. Now for b, we see the base of the logarithm is 5. 5 to the power t, because the output of the logarithm becomes the input of the exponential, is equal to y. Similarly, for ln of b equals negative 11, we know when it's just ln and nothing's written, that's actually hiding a log base e. We just give it a special notation for efficiency's sake since it's often used. So to write this as an exponential, we would have the base e raised to the negative 11th power equals b, and we see that the input of the logarithm, or the output of the logarithm, becomes the input of the exponential. The input of the logarithm becomes the output of the exponential. So that's a pattern that's going to keep happening, specifically because these are inverse functions of each other. Now, sometimes logarithms, since we can rewrite them as exponentials, we can evaluate them even without the aid of a calculator. So for instance, if I was to evaluate our example in part A, I'm not sure what log base 4 of 16 is, so I'm just going to put this as a question mark, but then I'm going to translate it to its corresponding exponential. Because what do we know about logarithms? They're the inverse of exponentials, and between logarithms and exponentials, we know a lot more about exponential functions than logarithms, so it would benefit us to translate this first to an exponential. The base is 4. 4 to what power would give you 16, and if you think through your power rules, that would be 2. So this logarithm takes on the value 2, because 4 squared equals 16. Take a moment to translate similarly and attempt C. This would be a good time to pause your video, attempt it on your own similar to our previous example, and then unpause to check your work. So we do not know the value of this, so log base 2 of 8, not sure what that is. I'm just going to put a question mark so I can start working with this. I'm going to translate it into an exponential. 2 to what power would give me 8? As I think through this, that would be 2 cubed is 8. So this logarithm equals the value 3 because 2 cubed equals 8. Now for the next one, if we were to write this as an exponential, we don't know its value, but we have 1 to our unknown value would give us 71. But this is just not possible because 1 to any number stays 1. So this is not going to happen, and this logarithm value does not exist. So what this means is the original statement is just kind of nonsense. It doesn't work because 1 to any number is 1, so there's no way you can raise 1 to a number and end up with 71. For our next one, we're unsure of the value of this logarithm, but we can translate it to an exponential. 2 to what power would give me 1 over 8? Well, if I know 2 cubed gives me 8, that makes me think of 2 to the exponent negative 3, because we know that negative exponents send something to the denominator, so 2 to the negative 3 power is the same as 1 over 2 cubed, which would be 1 over 8. So we know the value of this logarithm is negative 3. Now we discussed e. E is a very interesting number. It will be important to remember that e can be approximated by about 2.718. So remember, e will always be represented by this number in our class. I recommend you take a moment to find that on your calculator as well. And if we ever want log base e, we're just going to write it as ln of x, and we would call that the natural log of x. Now let's talk about graphs of logarithmic functions. So here in the table, I have graphed the function 2 to the x, and it's a few points chosen here. And then below it is the inverse function log base 2 of x, and a few of its points chosen here. Now we know that for the same base, the exponential function and the logarithm are inverse functions. And indeed, if we take the value for f of x, notice when the input is negative 2, the output is 1/4. And do we see for the inverse function, when the input is 1/4, the corresponding output is -2. So we do see that we've just switched the inputs and outputs for each of these pairs. 0, 1, 1, 0, 1, 2, 2, 1, 2, 4, 4, 2, 3, 8, 8, 3. And that's because 2 to the x and log base 2 of x are inverse functions, which we studied previously. Now if we see this graphed, because we know the inputs and outputs switch, it's no surprise that the x and y coordinates are reversed for inverse functions, which is equivalent to being reflected over the y equals x line. So here's our equation for 2 to the x, our exponential function, and reflected perfectly over the line y equals x, we would get our logarithm log base 2 of x. Let's investigate the graphs of the function log base b of x. So our value of b needs to be positive and not equal to 1. Given that, then we know the following characteristics of the graph log base b of x. First of all, it's a one-to-one function. If a function is one-to-one, we know it has an inverse, and in this case, the inverse of log base b to the x is the exponential function b to the x. Now, logarithms have vertical asymptotes at x equals 0. And that makes sense, right? Because we know exponential functions have horizontal asymptotes at y equals 0, but for inverse functions they switch the x and y. So now logarithms should have vertical asymptotes at x equals 0. The domain is only the positive values, which, if we remember, matches the range of the exponential functions. The range of exponential functions are from 0 to infinity, so logarithms being their inverse should have their domains from 0 to infinity. The range is -infinity to infinity, which is equal to the domain of the exponential. So here we see the play between the inverse function's exponential function b to the x and the logarithm function b to the x, log base b of x. There's two key points in a logarithmic function. Every logarithmic function has the x-intercept 1, 0, so they all must pass through 1, 0. The second key point is related to the value of the base. Every other key point on the function will pass through b, 1. Now there is no y-intercept because we actually have a vertical asymptote at x equals 0. And then you know whether your logarithm is an increasing function or a decreasing function based on the value of b. If b is positive, it's increasing, and if b is greater than 1, it's increasing, and if b is between 0 and 1, it's decreasing. Now, based on the value of the base, the logarithm function is going to either stretch vertically or compress vertically, and it's all about these two key points. Let's consider two of these. We have log of x as our function y, and let's consider the function z as just natural log of x. Now in this case, the implied base here is 10, because whenever we don't write a base for log of x, that's implied base 10. And here the implied base is e, which is about 2.718. Now we know both of these points have to have the point 1, 0 that's told to us. And indeed we see that on the graph. They both pass through this key point 1, 0. But additionally, this graph also has to have the point b, 1. So 10, 1. And in this case, this would be e, 1, which would be about 2.718, so close to 3. So imagine for the function y equals log of x, it's got to go over 10 units before it can go up 1 unit, so it's going to be actually a very steep curve after it passes through 1, 0. However, natural log of x has the next point e, 1, so it has to go over e amount, which is about close to 3, or close to 4, no sorry, it's close to 3, 2.718, and it goes up 1. Which is why we see that it does not have to be as steep, because its rise over run are a lot closer, whereas log base 10 of x had to run over 10 before it could rise up 1. So if you're given a lot of logarithms graphed together, you can tell that the larger the base of the logarithm, the closer it's going to be to the x-axis. The smaller the base of the logarithm, the higher it's going to be because of these key points. So here we're asked to graph log base 1/3 of x. So there's a few things we know. First, we know that every logarithm would have a vertical asymptote at x equals 0, so I'm just going to draw that immediately. Draw the things that we know for sure. Now, since the base is 1/3 and it's between 0 and 1, we know our graph is going to be decreasing, so we're just keeping that in mind as well. Every logarithm has to have the point 1, 0, so we know we pass through this point, and it's decreasing, so it's going to look something like this. But let's figure out specifically where. We would need to plug in a few key points. Additionally, we know that the point we've got 1, 0, but we also have the point, the base value, 1. So that would be 1/3, 1, so we can graph that as well. So at 1/3, we were at height 1, and in my case I'm going 1 is 2 dashed lines, so that would be our value for 1. And we know since it approaches a vertical asymptote, we could go like this, smoothly connected there, and then it continues like that, because we know our graph has to look something like this because we've got the base less than 1. So for these exponential functions, we actually don't need to make a table of values. If we keep in mind the value of the base and whether that tells us if it's increasing or decreasing, if we remember the vertical asymptote at x equals 0, and if we are able to find our two key points and plot those carefully on the graph, then we can connect it with the expected shape of the curve based on the value of the base. Next, we're asked to graph log base 2 of x. I recommend you first plot everything you know for sure about the function, and then you think about the two key points and you graph the function. Pause the video and attempt this on your own. Reference your notes as needed previous to this, and then unpause to check your answer. Now the base is 2, which is greater than 1, so I know my function's going to be increasing. Specifically, I know that the function would look something like this, an increasing logarithm. Now we've got two key points. We know we always have the point 1, 0 for logarithms, and then next we have the point base, 1. The base here is 2. So this would be 2, 1. We can plot these points. We know that a logarithm has a vertical asymptote at y equals 0, so I plot that first. 1, 0 is a point, and then you can go over 2 and up 1 is another point, and since I know the general shape of this logarithm and I know that it's increasing, I can complete the graph just based on those 2 points. Now before we get to our last question, let's remind ourselves the domain of f of x, which is equal to log of any base of x, is only the positive numbers. And we saw it on our graphs. They were only graphed from x is greater than 0 out to infinity. So in general, we know that the domain of a logarithm is 0 to infinity, but how could we deal with logarithms like this? This is tying together the knowledge that we learned during our domain portion of the class, composition of functions, and logarithms. So we're kind of knitting all that together now. We could view this as a composition of functions where the inside function is this 3x plus 2 over x. What function is it inside of? It's inside of the function natural log of x. So if g of x is ln of x and h of x is 3x plus 2 over x, then the composition g of h of x would give us our function f of x that we're looking at here. So this just makes our composition clear. And now we need to think about how do we find the domain of a composition of functions. If we go back to our 1.2 notes, we can see that to find the domain of a function composition, you first find the domain of the inside function and note any restrictions. Next, you construct the composition and you find the domain of this new function. If there's an overlap between the restrictions, use the most restrictive domain. So keeping this in mind, let's find the domain of ln of 3x plus 2 divided by x. Sorry, that should be an x there, not a 2. So first step, we find the domain of the inside function, which is 3x plus 2 over x. Now this is review information from before, so why don't we pause the video and you write down this domain, unpause to check your work. This can just help keep things fresh in our minds. Looking at this function, I would describe it as a fraction of 3x plus 2 divided by x. Now, 3x plus 2 has no problems because it's a polynomial, neither does x. The issue comes from the location of the x, because we know since we have a fraction, the denominator cannot equal 0. So the only constraint we need to think about is that x can't be 0, but that would include everything except 0. So the domain of this is from negative infinity up to 0, not including it, union 0, all the way to positive infinity. Because we've taken care of the denominator can't be 0. By itself, 3x plus 2 has no problems. By itself, x has no problems, except for the fact that it's in the denominator. Now step 2 is to form the composition. Our composition was ln of 3x plus 2 divided by x. And we ask ourselves, what is this domain? Well, we know that natural log can only take positive numbers. And the input to the natural log is normally just simply x. But in this case, do we see the input to the natural log is this 3x plus 2 over x? So whatever this 3x plus 2 over x is, since it's inside the function natural log of x, it has to be positive, because natural logs, along with any logarithm, can only take positive values. This would lead me to make the statement that we have to have the 3x plus 2 divided by x a positive number, strictly greater than 0. And we need to solve to see when this is true. Now this is what's called a rational inequality, and the way we might think about it is, do we see there might be different times when 3x plus 2 is positive or negative and where x is positive or negative? But we know the only way for the whole fraction to stay positive is if the top is positive and the bottom is positive, because positive divided by positive stays positive, or alternatively, the top is negative and the bottom is also negative, because negative divided by negative stays negative. What we can't have occur is the top being positive and the bottom being negative. That would send the whole fraction negative. Or the top negative and the bottom negative. That would send the whole fraction negative. But how do we find these points of trade over where here the top is positive, here the bottom is positive? We find those about the places where the top and bottom separately equal 0. This is called the idea of a rational inequality. And the way you would recognize it is you would have a fraction with the inequality related to 0. So when we've got a fraction with the inequality related to 0, we need to solve it with the following steps. We first find where the top and bottom equal 0 separately. So in this case, I'm going to set up the equation 3x plus 2 equals 0, x equals 0. So x equals 0 is simple, just that x equals 0. For 3x plus 2, I'm going to subtract 2 from both sides, divide by 3, and after a little bit of work, I would get x is equal to negative 2 divided by 3. And then what we need to do is step 2 is to make our number lines. These number lines are going to tell us exactly where is one expression positive and where's the other one negative. So I'm going to draw 2 number lines. And I'm going to label each of them. We need to label our work to stay consistent, so this will be the 3x plus 2, and this will be the x. And then you put the key points on each of the respective number lines, so I'm going to have negative 2/3 for my 3x plus 2 marked. And then I'm going to try to mark them with scale. This is negative, so the 0 should be past that to the right. So for x, I'm going to mark 0. And do we see that this splits the first number line into two pieces? Those pieces before negative 2/3, those pieces after negative 2/3. We know at negative 2/3 the function is taking on the value 0. So we wanted to see if before negative 2/3 the function's positive and negative, after 2/3 whether it's positive or negative. So let's pick a number before negative 2/3. That might be maybe negative 5. We're going to plug negative 5 into the equation, so 3 times negative 5 plus 2, that would be negative 15 plus 2, negative 13. We don't really care what it is, but we do care that it's negative. So that means this whole section before negative 2/3 contributes a negative output if you plug it into the equation 3x plus 2. Picking a value to the right, we could actually pick the value 0, that's to the right. And we see if we plug in 0 for our x value, we would get 0 plus 2, which is a positive. So that means for all x values after negative 2/3, 3x plus 2 remains positive. Now let's just verify what's occurring with our function x. We know x is more simple to think about. For negative values of x, it's negative. For positive values of x, it's positive, so this is negative and positive. So if the entire fraction is going to be positive, then we need to consider what parts of these intervals are they both positive or both negative. So here we see that 3x plus 2 over x is positive when, looking at our number line, we see that when you're before negative 2/3 in both circumstances, do you see we had two negatives? Now in this one we were before negative 2/3, and this one we're before 0, but they do have to overlap, so we kind of have to cut it off at negative 2/3. Before that they're both negative, so the fraction would be positive. So that would be from negative infinity up to negative 2/3. Union, okay? Now we do not want to be between negative 2/3 and 0, because for 3x plus 2 that would give you a negative value. Oh, sorry. We don't want to be between negative 2/3 and 0 because that would give you a positive value for 3x plus 2, but a negative value for the denominator. Positive divided by negative is still negative. So that moves us on to past 0. Now past 0 for the top is positive, and past 0 from the bottom is also positive. Positive divided by positive stays positive. So we're also going to union from 0 on to infinity. No other places in the interval would make this fraction positive, because we do need to have the top being positive divided by the bottom positive, or the top negative divided by the bottom negative. So that's the domain restrictions for ln of 3x plus 2, but then we know step 3 is to combine all the restrictions together. So in step 3, we are now going to consider, we had a few restrictions from the first. We had x can't be 0. And from the second, we had this domain restriction, because what's inside the logarithm can't be negative. And we ask ourselves, do we need to restrict it? Well, the first one says that x can't be negative, but do we see that's naturally implied in the second one as well, because we are not including 0. This is an open bracket, not a closed bracket. So we're already avoiding x equals 0 there. So our overall domain will just be from negative infinity to negative 2/3, union 0 to positive infinity. Let's just review the steps of this one more time. The key idea is that we know logarithms domain have to only be positive numbers as the input, but in this particular example, our input was quite a bit more complicated than usual. So whatever this input was had to be okay for itself, which meant that x can't be 0, And additionally, the overall value of the input needed to be positive so that when it gets inputted into the logarithm, we don't have a domain error. So we already knew that just by itself, x couldn't be 0 because we couldn't let the denominator of a fraction be 0. And then we said, what could be the problem here? Well, this needs to be positive because the inside has to be positive in a logarithm. That took us to solve this rational inequality, which we solved with all of this effort here. So we found where both the top and the bottom equal 0. We set up our number lines and we plugged in values before and after our 0 points to determine the behavior of each of the functions before and after. Before negative 2/3, the 3x plus 2 was negative. After the negative 2/3, the 3x plus 2 is positive. Before 0, x is negative. After 0, it's positive. So then we correlated when are they either both positive or both negative, and we came up with this description. And then in terms of the domain of a composition, we know after you figure out the domain of the inside and you form the composition and find the domain of the composition, then you have to compare both of them and say, do I need to restrict things further? In this case, they already are included in each other. If x can't equal 0, that's okay by this because we are not including 0, we are just approaching it. So our final domain of the original function was this.